All right, let's get right into it. If you're prepping for a competitive civil engineering exam, you know reinforced cement concrete, or RCC, is going to be on there. It's a given. So, over the next few minutes, we're going to break down the exact numbers, codes, and ratios you absolutely cannot afford to get wrong.
So, what are those things you just have to know? What are the numbers and codes that examiners love to throw at you? That's what we're here to do. We're cutting out all the noise and focusing only on the high-yield info that's going to get you those crucial marks.
First things first. Before we even dream of mixing concrete, we've got to know the rules of the game. And in civil engineering, that means knowing your Indian standard codes. Think of these as the official playbook for pretty much everything we build.
Okay, think of this as your cheat sheet for the codes. Now, IS 456, that's your Bible for plain and reinforced concrete. You're going to see it everywhere. But, for special jobs, you need special tools. That's where IS 1893 comes in for earthquake-resistant design, and IS 1343 is your go-to for pre-stressed concrete. A super common exam question is just matching the code to what it's for. So this table right here, it's your first major takeaway.
All right, rules are down. Now let's actually talk about what goes into the concrete. The final strength of any structure you build literally starts with these basic building blocks.
It's actually a surprisingly simple recipe, right? Just 4 main things. You've got cement, that's the binder, the glue that holds it all together. Then you have your fine and coarse aggregates, which is basically just a fancy way of saying sand and gravel. They act as the filler. And finally, you have water, which is the catalyst that kicks off the whole shebang.
Okay, let's get super specific here, because exams are all about the details. According to IS 383, fine aggregate is anything with a particle size less than 4.75 millimeters. So basically, it's the sand in our mix. And on the flip side, you've got coarse aggregate. That's anything 4.75 millimeters or bigger. This is your gravel. And that number, 4.75 millimeters, that's the magic number. It's the dividing line. And trust me, it's a classic exam question. Burn it into your brain. Now, this right here, this is probably the most important part. This table from IS 456 is pure exam gold, so really pay attention. It shows you the standard recipes for different grades of concrete. So let's look at M15, a really common one. You see that ratio? 1, 2, 4? That means 1 part cement, 2 parts fine aggregate, and 4 parts coarse aggregate. Simple. Now notice the trend. As you go down to a stronger grade like M25, the ratio changes to 1, 1, 2. See that? You're using a lot more cement compared to the aggregates. That's the key relationship to remember. So you see M20 written everywhere. But what does it actually mean? It's pretty straightforward. The M just stands for mix. And the number, the 20, well, that's the goal. It's the target compressive strength in newtons per square millimeter that the concrete should have after curing for 28 days. So M20 concrete should hit 20 newtons per millimeter square of strength.
And this is the key takeaway from that table. The richer the mix, meaning the more cement you have compared to the sand and gravel, like in an M25 mix, the stronger the concrete will be. It's simple, really. More of that cement glue means a stronger final product.
Okay, let's talk about the magic ingredient that kicks everything off, water. Its job is way more than just making everything wet. It's a chemical activator, it's a lubricant, and getting the amount just right is absolutely 100% critical.
So water really has 2 main jobs. The first one, and this is the most important, is hydration. This is a chemical reaction where the water and cement basically lock arms and create the bonds that give concrete all of its strength. The second job is to provide workability, making the mix fluid enough so we can actually pour it and compact it without any problems.
Now, here's something you really need to remember about that hydration reaction. It's exothermic. What does that mean? It means it gives off heat, a lot of it. In really big concrete pours, you actually have to manage that heat. Otherwise, you can get these things called thermal cracks, which are really bad for the structure. So, what's the absolute bare minimum amount of water we need for this reaction to happen completely? In theory, the water-to-cement ratio needed is somewhere between 0.23 and 0.25. This little range is pure exam gold. They love to ask this. Any water you add beyond this amount is just for workability. It's not making the concrete chemically stronger.
And that brings us to this constant balancing act. On one hand, if you go crazy with the water, all that extra water eventually evaporates. It leaves behind tiny little holes, or pores, and that makes your concrete weaker, a lot weaker. But on the other hand, if you're too stingy with the water, the mix is going to be super stiff, and you won't be able to compact it properly, which also creates holes and weak spots. So getting that ratio just right is everything.
So we've established that the quantity of water is a huge deal. But guess what? The quality is just as important. If you use dirty or impure water, you're setting yourself up for some disastrous long-term consequences, not just for the concrete, but for the steel hiding inside it.
Okay, get ready to screenshot this one. This is another critical table, straight from IS 456, and it tells you the absolute maximum limits for impurities in your water. Things like organic stuff or sulfates can mess with the hydration reaction. Suspended solids, they just create weak spots. And chlorides, oh boy, we need to talk about chlorides. These numbers are prime exam material, so make sure you know them. All right, listen up, because this is where a lot of people get tripped up on exams. Out of all those numbers on the last slide, the one you need to laser focus on is the limit for chlorides. The rules here get very specific, and it's a perfect trap for an exam question.
Here's the deal. For any concrete that has steel inside it, doesn't matter if it's regular old RCC or high-tech pre-stressed concrete, the limit for chlorides is a super strict 500 milligrams per liter. Why so strict? It's simple. Chlorides are like kryptonite for steel. They cause rust and corrosion from the inside out, and that can be catastrophic. It's a non-negotiable safety limit.
Whew, okay. That was a lot of numbers, a lot of codes. So let's boil it all down into 3 simple, memorable pillars for making quality reinforced concrete.
It all comes down to this. Number 1, get your materials right. Make sure your aggregates meet those IS code requirements. Number 2, get your proportions right. Use the standard mix designs from IS 456. And number 3, quality control. Be obsessed with getting the water-cement ratio correct and ensuring your water is clean. If you nailed these 3 things, you're building something that will last.
So there you have it, the fundamental blueprint for making good, strong concrete, according to the rulebook. But here's a final thought to leave you with. Making the material is just step 1. The real question is, how does this stuff actually behave when it's holding up a building during the incredible forces of an earthquake? That's where the real engineering begins.